So, hello everyone, my name is Paolo Forte and I'm a PhD student at the European University in Sweden. As you can see, and also as we discussed, I'm part of 2 labs there, so a lot of stuff to do, and I also... Is closed? Prova. Yes, now it works. Yeah, sorry. And also, I've been working, I worked for Novatron, and now I'm currently in Austria, working at Liber. So we will see what is my topic today, and I decided to call my presentation to optimal autonomous material flow and beyond, because we will see what does it mean to move material and to do it optimally, and what it requires. So what problem we need to solve. So we will see like some different topic here, because of course, if you think about how we can move material from one place to another, we do a lot of different stuff, because there are different problems that need to be solved. And here you can see a kind of a book that I'm kind of also writing for what is my PhD. So we can summarize it in this book where we have different chapters, and each of these has a different topic that I'm currently investigating. So the problem that we are kind of focusing on is this one. So we are in a construction site, and of course there are a lot of machines that need to be used to do different stuff. So there are excavator, wheel loader, bulldozer, and so on. So as you can see, this is a very difficult problem. Why? Because each of these machines is kind of complex to use, and then we need to do is we want that these machines are autonomous. So they need to do all the tasks autonomously. And of course, what we also have is that we have material that we need to move, and the material is not something like a block, so it's not something discrete that you can easily move with all other topic, like, I don't know, as pallet, for example, that maybe is more easy to move. But in this case, we have continuous material, so it's difficult to grab, and there is a lot of study behind that. And then, of course, in this side, we also have machines that cooperate between them, so we need also to consider that. So as you can see, there is a lot of problems, so we can solve it like that need to be solved. A lot of research that need to be done. And of course, you need also to consider that you have a dynamic environment. What does it mean? That every time you do something, this affects also the others. I mean, once a location is, you drill a location here, like here, you cannot do anything more here, because, I mean, other machine cannot access more that location. And of course, so it's, as you can see, you have a lot of uncertainty also. So I mean, like where the machine is, how much material you have loaded, and so on. So there are different problems, as I say, that need to be solved. So I think in our project, each of us focus on a different problem. So there are some focusing on the localization, on the mapping, on the control, and so on. And of course, I'm just focusing on one part of this, and that are the task allocation, the motion planning, and the coordination problem. Practically, what I'm doing in one sentence, I tell robot what to do and why they need to do that. So we start investigating the problem. As I said before, we start to thinking, okay, you know what? This problem is not that complex, because we can think as more like a Sokoban game, right? We need to move some stuff, and every time we move something, this affects the environment. It's like something like as a game. The problem is that in this case, as we said before, we have also to consider continuous material. So we need to consider how we can move the material and not as blocks, because otherwise it will be very, very simple to do. And so, first of all, what we need to do is we need to solve this problem. Why? Because we need to arrive to some goal configuration. So we start from different material placed somehow, like the different material that need to be placed with a certain criteria, and we want to reach this goal configuration. And of course, we want to move the material, but we also to move also as optimal as possible. So as you can see, there are a lot of topics to consider here, and I'm focusing more, as I said before, on just few of them. So let's start with the task planning. So this is a topic, because what we need to do is we need to plan the action. Because of course, if you are building a structure like this, you just have like some book that you can follow, and in order to reach this configuration here. Otherwise, you will reach another one if you don't follow that correctly. And of course, the action are planned in a predefined sequence that you need to follow. It's the same as here. So we need to define the action. So what we have done before is, okay, we just create a small problem. We have some machine, we have some important waypoint, loading, dumping, and so on. And so we say, okay, in each of these locations we have material. So how we can plan the problem? So how we can plan the action to move the material from one place to another? First of all, we say, okay, we start with the basic problem. Okay, we consider the material as blocks. This is like, we'll see then we introduce some problem that we'll see in the next slide. But then we say, okay, we can consider material as blocks, and so we start moving blocks around. And what we have seen, the problem here is that if you consider the material, how many blocks can represent this amount of material is difficult to understand, because, I mean, you can consider like as few blocks, as a large block, so it's one single block for all this material. The problem is that if you consider the pile of material, then you have like variable size of pile, variable shapes, and then you have material with different capacity. So whenever you're trying to move the blocks, then it becomes very complicated because, yeah, the planning problem is kind of very, very difficult. But then you say, okay, but what about small amount of material? So each block represents like a small amount of material. Yeah, then the problem becomes very crazy. So you need to write all of these conditions here manually and for each of these blocks. So if you have 100, you need to copy and paste the first line 100 times. And then you need to change one kind of part of this string here. So it's kind of very complicated, and you probably get some error because you need to be very, very, very precise. And for this, we also published a paper where we discussed exactly this problem. And so we say, okay, like, this is a problem, so we cannot consider really the materials blocks. I mean, it can be from one side not realistic, from the other too complex to resolve the problem later. And then we say, okay, we can consider the material as number. So this is like, is called a numerical fluent in the planning problem, and so it's just simply a variable like this increasing with numbers. The problem here, what is, like that whenever you want to build a road, also in the presentation from Andy, you see that you have specific lawyer and specific amount in each lawyer. So you need to be very precise when you leave the material there. And the problem here that we investigate is that whenever you load the material, you never know how much material you have loaded. The problem in the planning problem is that whenever you use this numerical fluent, you use the capacity of the material, it's supposed that the material load that capacity, but in reality this is not true, leading to then problem because you don't move the exact quantity of material that you want. And so then it will be a road that is not really a road. And yeah, after that, we start investigating how we can solve this problem here. And the solution that we decide to use for now is behavior trees. Behavior trees are very simple, and they're very, very used in this case because they can be used to create complex system, in this case also complex behavior that you can do. And how does it work? Very simple. There is like every time like there is some control node, and depending on the control node, you take each children in a different way. So you can think like about, we have a behavior tree to move the pile, and this has like 4 actions that need to be executed. So this is a special node that we developed that can loop all the, an action, a method in this case, that is the move the pile until a certain criteria is verified. So as you can see, you start to move to reach the load, you load the material, you move to the dump, and then you dump the material. And if then this criteria is not verified, then you start the loop again. So you go again to the move location, you load the material, and so on. And this continues until all the material is moved. What does it mean? This means that we don't have anymore the problem about how much material we load every time because we don't care. It's just we continue until we move all what we want to move. But also, in this case, it also means that we can also make very simple problem from a planning point of view because we don't need to care about numbers and so on. We can just put just one line that works. So as you can see, in this case, then it's verified. Then what we have done is, okay, but we can also think about using behavior tree for planning. And so in this case, we create a structure that uses behavior tree for doing all the planning. What does it mean? This means that this system is very dynamically adaptable to the situation, to the planning problem. So what this means that it computes a plan to move some materials or to reach a final configuration, and it dispatches the action itself. And whenever the action cannot be executed, it replans. So as you can see, this can be easily adapted to any kind of online replanning, and also thanks to the structure of the ESR3, of course. And then you can also execute the action until all your criteria is verified. So this is like a very good step, because if you want to move material autonomously, this system is able to do that, because of course, everything is needed to do that is here. Of course, there is a small step that needs to be done. That is, I need, of course, to execute this action here. So I need to navigate, and I need to then to do the loading and the dumping. For me, I'm not focusing on how the load and the dumping are done, but I'm more focusing on how I reach the location and how I can use this configuration here. So how I can tell like that the amount of material is moved. So regarding the navigation, what I've been working on was, okay, we have a dynamic environment, we have very complex machines that need to be moved, and we have very complex structure if we don't think about only the construction site, but also, for example, the mine. Because we can have like different area where maybe you need to use a different type of path planning strategy. So here you may use one, here in the corridor another one, and so on. So what we developed is a context-aware navigation system. What means context-aware? That you have some rules, and depending on this rule, you make some choice. So you choose one planner respect to another, because maybe it's more optimal, maybe because it's better to compute a plan, it's faster, and so on. And this is very good, because if you have this system, you first of all can overcome the limitation of single planner strategy, because you have multiple planners. So if one fails, you just choose another one and use that one. And then you can also optimize the planning, because maybe you find that in some part of the map here, you change planner because it's optimal for some reason, for curvature point of view, or maybe for a path planning point of view, and so on. And then, of course, you have a smoother navigation, because then you can use also path curvature and improve the drivability. So here is the structure that we developed. So we can see like the node that I added to the current navigation tool system in order to develop my system, where you are able to select a planner and select a control strategy. And then all this system, what it's doing is computing a plan and computing a path, following the path to the desired location. And this system receives some data, so receives some data from the segmented map of the environment that you have, receives some information from the LiDAR sensor that you have from the camera. And what it's doing is using this information to select what are the best global planner strategy and control strategy that you can use. And of course also to set navigation parameters. So maybe if it is foggy, as in this case, you need to reduce your velocity, because maybe you cannot see so far, so you need to be able to brake at any time. And here you can see also a simulation example that we have done, where you can see how the planners switch on different areas of the map. So you can see you move it from like lattice planner in the open area to grid-based approach in the corridors here. And we have been testing this with different also maps, and of course we have just implemented here to planner, but you can implement any planner that you want here. And we also been testing the system in unknown environment, so whenever you don't know the map, but you are currently only using your LiDAR information, and that's in this case the system works pretty well. So the drivability of the machine is quite well, despite here, because here is a bit a problem of the planning strategy that we decided to use. And then, of course, we also, as I said before, we also need to optimize the process. So we now know that how we can move the material. So we decide the action to move the material. We have seen the navigation, but also we need also to optimize this process, because of course, whenever you talk about this topic and you want to sell this topic, of course, you need to kind of prove that this is better what is the current situation nowadays. So for this, what I've developed is optimal task assignment system, where we have like two costs: the cost of a single robot here, and the cost then of the interference among the robots. So the fact that you have path here, that there is some interference among them, and so you need to decide which robot to go first, and of course this introduces some delay. You can use this system here in order to select which is the best task assignment that you can have. And this is like also a paper that we published in the RAL, so in the IEEE Robotics and Automation Letters. And here you can tune whatever you want to optimize, and this can be any type of cost. So the path length, any type of single robot cost, and this can be like any interference cost. So the productivity, it can be like the time delay, and so on. And also, after that, we also want to decide how many machines we want to use. So determine the optimal amount of machine. Because of course, the more machine you use, the less time that you need to complete a project, but also the cost increase. But also if you use less machine, of course, the time increase and maybe the cost decrease. So we want to find the optimal point, and so design what is the optimal number of machines that we need to use. And for doing that, I developed it's more like just a graphical interface that helps the user to define a problem, to define where the material is, how many machines do you want to use, and after that he's doing everything itself. So it decides the allocation of the robot, it suggests what is the optimal number of machines that you want to use, and so on. So you can easily specify everything, this graphical interface, and after that is everything up to the system. And after that, just what I'm thinking to do next is, of course, to optimize the plan that we've seen before, because, of course, then there's some criteria in order to optimize the plan, and also if we can introduce some learning. Because, of course, nowadays I'm currently providing the plan, the planning problem domain to the system, but I want to see if it's possible to provide them automatically to the system. So you just provide, I don't know, something basic, and then all the system is doing this itself. Then for the navigation part, instead I'm focusing about getting information from obstacles and maybe humans, and decide also that the planner that I want to use and the navigation parameter. And also in this case, how I can select the planner according to the operation that I want to do. Because maybe if I want to push something, or if I want to just doing other type of operation, maybe I need to use a different planner. Then about the optimization instead, what we want to do is optimize, of course, considering the different side of the machine, because now I consider just one side when I select the optimal number, and improve the fixed cost of the machine. So this is like more about how many machines I need to use. And then, of course, introducing cooperative tasks in the task assignment. And then we also been focusing on a multi-layer simulation system. So what is this? Is like a simulation where you can decide what level of simulation do you want to see. So it's very basic simulation just to prove, like, to test the planning strategy, a middle simulator to test the navigation, and the last one that use maybe fancy simulator like Gazebo algorithms in order to prove of course, your research. So that's been all. I think that I'm kind of also a bit early, so that's good. But if you want to test, if you want me ask anything, or if you want just to contact me, here you can find all my LinkedIn or GitHub pages and also my email. So thank you.
Any questions?
You mentioned that it's ongoing work or future work to learn to create a planning problem. And I guess you use the large language models for that already. Did you play around with this?
No. There was another PhD that I was going to involve from the Örebro University for that. Maybe I can get some work together in order to define that. Because, in that case, it's also difficult to understand how I can learn the planning problem, but it would be cool. Yeah. Let's see if I have time at the end.
So this was not the direction that you had in mind. So what was the direction?
So for example, if I have this, if I have like this scenario here, for example, where you have defined like, for example, this, I want to learn, like I want to define a planning problem. So like, what does it mean is that I have a file where I specified where this material is, where this material is, where this material is, where this machine is. But I want to do it like autonomously, so without me writing it. Or maybe I didn't get the question. No, maybe I don't. I didn't get it. Maybe if.
I guess the Achim question is more about a method than a problem, right? The problem is clear. You want to autonomously dispatch the tasks, but how do you want to solve it?
That's something that I will focus later.
Okay.
Yeah, no, that's
What I misunderstood was that this was in the end that was more about ongoing.
No, it's not ongoing. It's kind of future work that I want to focus about if I have time later.
Okay.
Because I'm a robotic guy and I like real machines. Do you have any ideas of kind of final demonstration with real machines to do this, other than the simulator stuff?
Yeah, at least for the navigation, yeah. For this one with the multi-fleet, I think it's kind of hard because you need a lot of robots to do that. But for the navigation part, yeah, if possible, I would like to do some experiment with a real machine.
So in this last slide with the future work, what was not there was anything about maybe improving runtime. And I don't know, how do you see this? Is the performance in this respect enough? Because even the simulation that you showed was sped up 6 times. So is this a problem?
That's a good question. I never worked on a machine, so I don't know, I cannot answer that. So I think that's why I want kind of to test with a real machine to see how things work. Because, as you said, in simulation it's also different. And everything looks fine maybe, but then when you run on a real machine, then nothing maybe works. Because, I don't know.
Just one comment and question. Maybe when you do task assignment, basically the machines, they don't have to be autonomous. They can have drivers, right?
Yeah. Right. So my topic here was also more about kind of an assistant system that you can use to decide just the plan, yeah. In this case, yeah.
Thank you.